Hello everyone, this is Shraddha Bhurre from IAPS DAV Indore. I'm going to explain some questions which is based on topic of numerical analysis and design, numerical differentiation, Simpson rule, forward difference and Gauss-Seidel method. Our first question is based on numerical differentiation. In this question we have to calculate df upon dx at x3 and d2f upon dx2 at x1. So first of all, we have to generate our difference table. By forward difference, the function value at the current argument is subtracted from function value at next argument. By this, we can generate our del f1, del f2 and so on, and del square f1 and del square f2 and so on. For numerical differentiation, we have to use interpolated polynomial. So here we assume this polynomial. In this polynomial, del f1 and del square f1 are forward differences and r of x is the error term which we will neglect in our solution. For calculating df upon dx at x3, first of all we have to calculate df upon dx. So this is df upon dx, and the value of del f1 and del square f1 from our difference table is, this is del f1 and this is del square f1, and h is the difference between interval, that is difference between 0.25 and 0.26 is 0.01. By substituting this value in above equation, we have our answer 0.9550 at of df upon dx at x3, that is at 0.27. Now for d2f upon dx2 at x1, we have to differentiate equation 1, double differentiate the equation 1. So here the double differentiation of equation 1. In this equation, del square f1 from our difference table, this is del square f1, and again h is the difference between our interval, that is 0.01. Now substituting these values in above equation, we have our answer -1 for d2f upon dx2 at x1. Now our next question is to integrate the function using Simpson rule. We know that Simpson rule require an odd number of points. Therefore we will use trapezoidal rule for the first two and the Simpson 1/3 rule for the rest. This is trapezoidal rule. In this trapezoidal rule, y0 is 4 and y1 and last term yn equals to 2. Now substituting this value in trapezoidal rule, we have this reduced function. In this we have integrated our function from -0.6 to -0.5. Now by Simpson 1/3 rule, this is the formula of Simpson 1/3 rule, and we can find the value of y0, y1 up to y8 from our table, and substituting these values in our formula, we have this reduced function. In this rule, we have integrated our function from -0.5 to 0.3. Now combining both rules, we have here our integrated function from -0.6 to 0.3, that is equals to 3.1. Now our next question is to estimate the population in the year 1925, 75 and 84. So in this question we'll use a forward difference formula and backward difference formula. First of all, we have to generate our difference table. Again, by forward difference, function value at current argument is subtracted from function value at next argument. By this, we can generate del f1, del f2 and so on, del square f1, del square f2 and so on, del cube f1 and del cube f2 and so on. Here del cube f is nearly 0. We can fit a quadratic and use only up to second differences. Now we have to estimate population in the year 1925. From our difference table, we can see that 1925 is top of the table. So we use forward difference formula. Here A is the starting year, that is 1921, and H is the difference between the interval, that is difference between 1921 and 1931. By substituting this in the formula, we can generate a u equal, here u is 0.4, and from difference table, f of a, 35 is f of a, 7 is del f of a, 9 is del square f of a. Now substituting this value in our forward difference formula, we have our result 37 for year 1925. Now we have to estimate the population in 1975. From our difference table, we can see that 1975 is near the bottom of the table, so we use backward difference formula. This is backward difference formula. This operator is backward difference operator, and here a plus nh is the last year, that is a plus nh. 1981 is our a plus nh, and the difference between interval is same as this, that is 10. By this we can generate our u, that is minus 0.6. From difference table, this is f of a plus nh, this is del square f of a plus nh, and this is this is del f of a plus nh, and this is del square f of a plus nh. Now substituting this value in backward difference formula, we have our result 186 for year 1975. Now we have to estimate the population in year 1984. In our difference table, we can see that 1984 is outside table, so we can't interpolate. So if we assume the trend outside the table is same as inside, then we can use the same polynomial. Again using backward difference formula and generating our u, here is 0.3. And from difference table, again we can find our value of f of a plus nh, del f of a plus nh, and del square f of a plus nh, and substituting this value in our formula, backward difference formula, and we have our result 244.8 for the year 1984. Now our last question is to solve the simultaneous equation by Gauss-Seidel method. First of all, we should ensure that convergence of iterative procedure by this ratio. This ratio is non-diagonal element upon diagonal element. This ratio must be less than 1 for convergence of our iterative procedure. So by taking the same sequence as given in question, we have this ratio, that is non-diagonal element upon diagonal element. This ratio here is greater than 1, so our iterative procedure will diverge by this sequence of equation. So now we are rearranging our rows or rearranging our equations so that our diagonal element have the highest value in that row. So the order of the rows will be this. Now again calculate the ratio, that is non-diagonal element upon diagonal element. In this case, the ratio is less than 1. That is, by this sequence of equation, our iterative procedure will converge. So now sequence of equation are this. Now we are calculating the values of x1, x2, and x3. So in first equation, first step, we have to substitute the value of x2 and x3 0 for generating the value of x1 in first iteration. This denotes the iteration number. So in first iteration, our x1 value is 0. Then this value of x1, that is 0, is substituted in equation 2, and 0 of x3 is calculated. Calculate value of x2 for first iteration, that is substituting value of x1 equals to 0 and x3 equals to 0 in equation 2 for find the value of x2 in first iteration. Now putting the value of x1, that is 0, and x2, that is 15 by 4 in equation 3rd for find the value of x3 for first iteration. So here is our value of x3 for first iteration is equals to minus 35 by 8 For second iteration, and this value of x2 and x3 by first iteration are used to calculate the value of x1 in second iteration. And the next step, the value of x1 from second iteration and x3 from first iteration are used to calculate x2 in second iteration for the equation from equation 2. We will continue to iterate till two iterations have nearly the same values for x1, x2 and x3. In this table, these are the values of our iterations for x1, x2 and x3. From the table we can conclude that iteration 8 and 9 have nearly the same values. This iteration 8 and 9 have nearly the same values. So value of x1, x2, x3 and 9 iteration 9 are required value of x1, x2 and x3 from three given equation. Hence our result for x1, x2, x3 are as follows. Thank you.